What we've got here is a straight line going down which represents a convex lens. Okay, so this is a convex lens which is converging. Perpendicular to that is this line here which goes straight through the middle, which we call the principal axis, which you should remember from GCSE. And we've got 4 dots. Now the 4 dots, the first dot here represents the focal point. Now remember, on a converging lens, parallel beams of light will be converged through the focal point. That's important for how we construct the ray diagram. And so therefore this distance between the lens and the point is the focal length of the lens, in this case 3 centimetres. This dot just represents a distance of 2f away from the lens, so that's 6 centimetres. Here is, and don't forget that light can pass through the lens in both directions, so we have to define the focal point on this side and a distance of 2f away from the lens as well. So we've got 2f, f, f, 2f, convex lens, principal axis. Now this object here represents an object. Any object. I've simplified it by just using a line. We're going to pretend that all the light is scattered off the top of the object. So light comes in, it's scattered off the top of the object. Obviously it's scattered off all of the object in many, many different directions and goes through the lens. But obviously we just want to simplify it, and we're just going to consider the light that scatters off the top, and we're only going to consider 3 beams of light. Okay. In fact, later on I'll only consider 2 beams of light, but I just want to show you on the first one 3 beams of light. Okay, so this is what I want to do. I want to consider a light beam that hits the top of the image and is scattered parallel to the principal axis. Now, as you know from class the other day, that such a beam will be focused through the focal point of the lens. That's something that we spoke about the other day, and you should know from GCSE. So the first thing I'm going to do is draw that. I'm going to draw that line which represents a beam scattered parallel to the principal axis. Now, my beam is not very accurate at all. When you guys do this, you have to be incredibly accurate when doing these diagrams. You can't be as inaccurate as I have there. I hope you understand that the software isn't quite good enough to do this properly. Now, what happens to this beam? It hits don't forget my arrow to show the direction of the ray. The ray hits the convex lens. Convex lens converges the light through the focal point. Only parallel beams of light through the focal point. So what happens is I have to draw that beam being refracted straight through the focal point of my principal axis. Now, if you note, that's not actually good enough. I have not done that well enough because it's not going. But this is just the principle of the is the idea. Now, the next beam that I'm going to consider, add an arrow to show the direction. The next beam I'm going to consider is a beam that's scattered off the top of the object, and it goes straight through the middle of my lens. It goes straight through the middle. Now, as we spoke about in class, and I'm sure we all know this from GCSE, a beam that goes through the middle of the lens doesn't get refracted at all. In fact, it does get refracted, but the net effect of the refraction is that the beam just goes straight through. And that's true every time you do a ray diagram. So I take the ruler and I draw the ray going straight through the middle of the lens. Okay. Now what you notice is that the beams intersect at this point. Now think about what that means. If I was to put a screen at that point there, all the light from this light beam and this light beam, which are showing the same thing, which are light from the same, scattered from the same point, meet here. I'll get a clear, sharp image of the top of my object at this point, because that's where the 2 beams meet. If I was to put a screen here, then the image from the top beam would be in a different place from the image of the bottom beam. Therefore, 2 images of the top of my object would be created, and therefore it would cause a blurred effect. I get a clear, sharp image when all light rays from the same point on the object intersect at the same point here. So the best place to put my screen would be here. Now, just to show you, hopefully this will work, that it happens for all the light beams, or the light rays I should say, consider another one, a third one, which scatters off my object but happens to pass through the focal point on the near side of the lens, okay, and then hits the lens. Now what happens here is the converse of what happens on the top. If it goes through the focal point here, it will get refracted parallel to the principal axis. So it comes out, and it's just a little bit wrong, but you get the idea. It gets out and it's refracted parallel, and hey presto, it goes through the same point. Now if you were to do that very accurately, unlike I have here, you will see that every single time you do this, all three beams will go through the same point. So step by step, step one is to draw the parallel beam, refract it through the focal point. Step two is to draw the ray that goes straight through the middle of the lens, and step three is to draw the ray which goes to the near focal point and then is refracted parallel to the principal axis. And that's how you construct a ray diagram. Now, what about the image? What you'll notice is the image will be produced here. So my image is actually here. If this is my object pointing upwards, my image is pointing downwards. Okay? Incredibly important situation. The lens has produced an image which is smaller than the original object, which is perfect. That's how our eye works. Our eyes produce an image that is smaller than the original object. And that's how we manage to see things which are much bigger than our eye. That's how I can see another person who's 2 meters tall, because the image on the back of my eyeball is so small. Now, you guys have to be able to recreate these diagrams, and you also have to be able to describe the image that they produce. Now, there's 3 different things you have to mention. First thing is magnification. Has the image been magnified? Well, the answer is no. It's actually been diminished in this case. It's actually been made smaller. It has been magnified by a factor of less than 1. So we say the image has been diminished. Okay? Now, magnification I can actually measure, okay? Because the object is actually 2.5 centimeters tall, and the image is only 1.1 centimeters tall. So, to be able to calculate the magnification, what we do is we say the magnification is image height all over object height, which in this case is 1.1 all over 2.5. So, which is going to be less than 1. I don't have my calculator on me, I'm sure you could do that yourselves. That's what we call the magnification. So our image has been diminished. The second thing I need to do to describe it is to say, so step 2 is to say whether or not it's been inverted, i.e. flipped upside down. And in this case it has, so it's been inverted. Okay? And the step 3 is to say whether or not the image is real or virtual. Now, this is a real image. Why is it a real image? 2 reasons. If I was to put a screen here, I would actually physically see a projection of the object. I would be able to see a picture, just like an experiment you did the other day, where you saw a picture of the crosshairs. This here would be a picture of my object. That's how we see it, see things. A picture is actually projected onto the back of our eyeball. The other thing is that to say that it's a real image is that actual light rays are actually producing the image. So it's a real image. Okay?